Hi GOR, this is a video of lesson 12, proofs of various circle theorems. So what we're going to do is we're going to take some of the things that we learned about circles and apply them to some of the things we learned when doing our triangle proofs earlier in the year. So for example 1, I want to prove the theorem congruent chords define central angles equal in measure. So there's not really a given and a proof, but the given is this congruent chords, so I know the chords are congruent. If we look at the picture, I have the chords highlighted in yellow. So the chords are A, B, and C, D. So the given is that those two chords are congruent already. What I want to prove is I want to prove these central angles are equal. So what's a central angle? Angle AOB, where I have this red dot, and angle COD, where I have this red dot. This is what I'm trying to prove. I'm trying to prove the angles right there are congruent if the chords are congruent. So what I'm going to do is I'm going to prove these two triangles are congruent. And if the two triangles are congruent, then these corresponding angles have to be congruent by CPCTC. So remember, I start off my proof with statements and reasons. So step 1 is always the given. The given is AB is congruent to CD. All right, that's the given. Those are the chords. Now look at step 2 because that's a brand new step for us. Step 2 says that AO is congruent to BO, is congruent to CO, is congruent to DO. And I have those all highlighted in blue on the picture for us. And if you look at them, all of those are the radius of the circle. And the radius of the circle, no matter where you draw it, has to be the same length. So I don't know what this length is, but whatever BO is, AO has to be the same thing. So all of these sides are congruent to each other, and I've marked them congruent. Now, the reason in the proof is that all radii, so that's just a plural for radiuses, all radii in a circle are congruent. Okay, now I remember I said that my goal was to get these two triangles congruent to each other, and I actually can say that the triangles are congruent. The triangles are congruent by side, 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 because I had the chords that were congruent, the yellow highlighted segments, and now I know that all the radiuses are congruent. So I have side, side, side in this triangle, congruent to side, side, side in that triangle. So triangle AOB is congruent to triangle COD, and the reason is side, side, side. Now, once the triangles are congruent, I can say that all of the corresponding parts are congruent. So I really wanted to say that angle COD is congruent to angle AOB. Those are the central angles. And the reason that they're congruent is CPCTC. Corresponding parts of congruent triangles are congruent. Okay, if you need to pause the video to write anything down, please do that. We're going to move over to example 2. Now in example 2, they're telling us that BC, which is this diameter here, is perpendicular to DE, which is a chord. FA is 6, so I wrote in the 6. AC is 10. Now AC, look at AC. AC is the radius of the circle. AB is also the radius of the circle. So if I know the radius of the circle, AC is 10, then that means that AB also has to be 10, a radius. And I know that AF is 6, so 10 minus 6 is 4. And I wrote that over here. So I know that AC is 10. They want me to find BF, which I actually just did, and DE. Explain your work. And there's a little hint there to connect A to D and A to E. I actually just connected A to D, but I can also connect this other one over here, although I don't know if it's necessary for what I am doing. But let me just connect that, right? And they want me to connect A to E. Okay. So the first thing I want to do is I want to find BF. Okay, so right here, BF, this little piece right there. Let me get my highlighter out. I can highlight that in green for us. So they want me to find BF. BF is part of the radius BA, and we already know that a radius is 10 because I know that AC is 10. So BF, which is this little green section, plus FA equal the radius, so it has to equal 10. And in the given, they told me AF was 6. So 10 minus 6 is equal to 4. So BF is equal to 4. Next thing I want to do is I want to find, what is it? DE. All right, so DE is this whole line here. Let me get a highlighter. I want to find the length of this whole line DE. Now, I'm not going to actually do that all at once. I am going to first just concentrate on the facts. Let me get a little highlighter here. This right here is a right triangle. Now, how do I know it's a right triangle? Remember back in the given, they told me that BC is perpendicular to DE. So this is a right angle right there. I know this is 6 because they told me that. AD is just another radius, so AD is 10. So I can find DF and then double it to find DE. How am I going to find DF? I call this little segment right here X. X squared plus 6 squared equals 10 squared. I'm going to use the Pythagorean theorem because I'm missing a side of a right triangle. So I have that right here. 6 squared plus x squared equals 10 squared. Now 6 squared is 36. 10 squared is 100. I'm going to solve for x squared, so I'm going to subtract 36 right here on the left. But whatever I do to the left, I have to do to the right. So 100 minus 36 is 64. And in order to get x by itself, I'm going to take the square root. Okay, in order to get x by itself, I have x squared. I have to take the square root. So the square root of x squared is x, and the square root of 64 is 8. Now that's actually I have a mistake right here. That's DF. All right, I need to find DE. So I'm actually going to have to do 2 times 8 in order to find that. So DE equals 2 times 8, which is 16. Okay, so that's my answer right there, 16. I'll circle that for us in red, because when I found this down here, that was actually DF, not DE. So this is DF. Okay, so that's example 2. Example 3, I'm going to be talking about ratios. Ratios, I know some people don't like them, but they're actually pretty easy. So I know the measure of arc BD to the measure of arc DE to the measure of arc EC is in the ratio 1 to 3 to 5. So I just simply call the first one is BD, I call that 1x. The second one is DE, that has a ratio of 3, so I call that 3x. The third one, 5, so EC has a ratio of 5x. So I have that all highlighted right here in the matching colors so you can see which is what. BD is 1x, DE is 3x, and EC is 5x. Now, can you see that all 3 of those arcs together form a semicircle? So think about what that equals in terms of degrees. A full circle is 360 degrees, so a semicircle would be 180 degrees. So all of these arcs together equal 180 degrees. So I just write an equation, 1x plus 3x plus 5x equals 180. 9x equals 180. So x equals 2 because I divide both sides by 9. Knowing that, I can now substitute in. 1 times 20 is 20. 3 times 20 is 60. 5 times 20 is 100. And I know this side over here is another semicircle, that's 180. So now I have all the arcs of the circle, and I can look at the questions and see what I need to find out. So A just wants me to find the arc of BD. Well, that's the one I have highlighted in yellow, and that's just 20. B wants me to find the arc of DEC. So basically I'm taking DE and I'm taking EC and I'm adding them together. So I highlighted them in green. So the DE is 60 and EC is 100. So DEC is both of those together. So DEC is 160. And then the last question wants me to find arc ECB. So ECB, let me get my highlighter here. ECB starts here, but then it's also this. So it's everything in that purpley color. So I have to add the 100 plus the 180, and that's how I get 280. Okay, again, if you need to pause the video in order to write anything down, please do so. Okay, turning over to the next page. Circles are similar. Explain how we can prove this. Now, this is going back to, I don't know, probably the beginning of the winter. We talked about similar figures. Figures are similar if there's a similarity transformation that maps one onto the other. Is a way I can map this triangle onto this triangle. Absolutely. I can translate it. So now the triangles are sitting on top of each other, but this one would be a little bit smaller then. So after the translation, I would have to dilate it until they were the same size, until their radiuses were the same size. Now, I'm not really dilating the angle, I'm dilating the length of the radius. So I would have to know the radiuses in order to figure out what that scale factor is for the dilation. But the key concept is that all circles are similar. And the reason they're similar is there's a similarity transformation that maps one onto the other. And that similarity transformation is a translation until one circle's on top of the other, and then a dilation until their radiuses are the exact same size. And these questions are basically the same. Are all circles similar? Yes. There's a similarity transformation that maps one onto the other, a translation and a dilation. So you don't even need to have this angle of 70 degrees shown. All circles are similar. So the fact that they're similar really has nothing to do with these central angles of 70 degrees. What similarity transformation maps all circles onto one another? A translation and then a dilation. Okay, and then we have another problem down here dealing with arcs and ratios. So again, I highlighted so you can see everything matches up. So BC is the first arc, so that's going to match up with 1x. CE in green is the second arc, so that's going to be 2x. I have that on the circle also. ED is the third arc, so that's my 3x, and I have that in blue. And then DB is the fourth arc, and that's my 4x. All of these arcs together, see the yellow, the green, the blue, the pink, they form a complete circle. So together, those arcs are going to equal 360 degrees. Okay, so that's important. Add these up. 4x plus 3x is 7x, plus 2x is 9x, plus 1x is 10x. So 10x equals 360. I divide by 10, and x is 36. Now that I know x is 36, I just went back in and substituted. 1 times 36 is 36. 2 times 36 is 72. 3 times 36 is 108. And 4 times 36 is 144. So you can use your calculator for that. That makes each of these angles is a central angle. So if the arc is 144, so is the angle. This arc is 36, so is the central angle. This arc is 72, so is the central angle. And the last one, if this arc is 108, this central angle is also 108. So then I have a bunch of questions here. The first one, I want to find the measure of angle BAC. So BAC is this one right here, BAC, where I have the red dot. So the central angle is equal to the arc. So if the arc was 36, then the central angle is also 36 right here. Angle DAE. So DAE is right here, DAE. Okay, DAE, I'll trace it in red for us. So that's also a central angle. It equals the arc. If the arc is 108, then that central angle is 108. Arc DB. So arc DB is right here. That was my 4x, and I know that x is 36. So 4 times 36 is 144. Another way to find it is that this is a diameter. And if this arc was 36, together this is a semicircle. So 180 minus 36 is 144. So there's just two different ways to do it, but you can see that we get the same answer. And the last one is arc CED. So CED are just these two arcs added together. Get my highlighter. So CED is CED, these two arcs. So I'm really just adding the 72 and the 108, and together that equals 180. And I sort of kind of knew that because this was a diameter right there. And if that's a diameter, then that is a semicircle. So that would be another way to get the same answer. Okay, my last problem. In circle B, AB is equal to CD. So I have AB highlighted in yellow. That is a radius of the circle, and it's equal to CD. CD is this chord. So basically the radius is equal to the chord. Well, if you look at this, BC, I'll do in a different color, is also a radius. So that has to be equal to AB. And BD is also a radius, so that has to be equal to AB. And if AB was equal to CD, then that means all of these sides are equal. So that makes this an equilateral triangle right here. And if it's an equilateral triangle, that means all of these angles are equal. So 180 degrees divided by 3, each of these angles is 60 degrees. Okay, so what the first question wants to know the measure of arc CD. So the measure of arc CD, that's this arc right here, is got to be 60 degrees. Why? Because this central angle is 60 degrees. If the central angle is 60 degrees, then the arc is 60 degrees. So that's the first question. Second question wants to know the measure of arc CAD. So CAD is actually going this way. CAD, I'll do that in green. So C, A, and then all the way to D. That's a major arc right there. So this whole thing in green. So this is 120 and this is 180. I'm going to add those two numbers together. 120 plus 180 is 300. Another way to do it is it's everything but this 60 degrees. So I could have done 360 minus 60, and that would also give me this 300 right here. And then the last question is the measure of arc AD, and the measure of arc AD is a semicircle. That's this one that I had right there. So AD is a semicircle, so it must be 180 degrees. Okay, and then this is just the work that I already mentioned, to find out that the fact that this was an equilateral triangle, all those sides are radiuses, so that makes all of them congruent. BCD is equilateral triangle. Why? Because all the sides are congruent, so all the angles are congruent, and all the angles would be 60 degrees. So that was just explaining what I already went through in the beginning. Okay, so starting tomorrow, you're then going to do the practice that's in your packet, and then we're going to do some review. You can use your notes as you're doing that practice.